Alright, today I'm going to explain some of the problems with the common eye, such as nearsightedness and farsightedness, why they happen, and how we can correct them using lenses. First off, I'm going to give you a quick rundown of the structure of the eye. The eyeball, everybody knows, is pretty much a spherical shape. It is a positive lens or a converging lens system where it actually refracts light from where it enters the eyeball to where it forms a real image on the retina at the back of the eyeball. Light first enters the eye through the cornea, which is a transparent tissue with a refractive index of about 1.376. The air-cornea interface is where about 75% of the total refraction of the light happens in the eye. After the light hits the cornea, it goes into the interior chamber, which is really just a chamber filled with some watery liquids that provide nutrients for the cornea. It has an index of refraction of about water, which is 1.33, but this chamber houses the iris, which is what controls the amount of light that comes in and out of the eye through the pupil. The muscles contract and allow the pupil to grow from 2 millimeters to about 8 millimeters to let different light pass through depending on the light stimuli. After the light passes through the pupil, it hits the crystalline lens, which is the main part of the eye. The crystalline lens is where the final fine-tuning light refraction process of the eye takes place. The lens can actually change curvature of the lens depending on the light and the object distance, which I will talk about a little bit later. It's called accommodation. But the ciliary muscles are the muscles that control the lens depending on the object distance. And after the light hits the lens, it passes through one more chamber, the posterior chamber, which is just again another chamber that's filled with liquids that nourish the eye. And then it reaches its destination, the retina, which is the part of the eye where the light turns from light energy into electrochemical energy. The retina has many layers, one of which contains photoreceptors that we know as rods and cones. The rods allow us to see better in the dark. They're more for night vision, and they don't have any color pigments, so the rods don't really determine what colors we see, while the cones function more in high intensity light, and they have color pigment, which allows us to see different shades of color. And then the final part of the eye is the optic nerve, which is just the part that transfers the light information to the brain so we can see images. Now, this here is Snell's law, and this demonstrates why we get the greatest amount of refraction at the cornea, because we have an index of refraction of 1, which is our N1 in this case, and the cornea index of refraction N2 is about 1.376. So this gives our greatest difference. All the other points of refraction are about 1.376, and then they range from like 1.33 in the chambers, and then the lens doesn't veer very far from this number as well. So this is where we get our largest amount of refraction. And given this example, we have an incident angle of about 45 degrees, and then as you can see from the math, Snell's law gives us a refraction angle of 31. So we're changing 14 degrees of refraction through the cornea interface. Now back to that topic that I was talking about of accommodation with the lens is depending on the object distance from the lens tenses or relaxes to change curvature so it can find focus on the retina, because unlike other objects, the eye has to focus on the same part every single time. It always has to hit that retina. It doesn't have the luxury of being able to change depth, so the lens actually has to change refraction to provide an image on the retina every time. So when you're viewing a more distant object, such as, I don't know, an object far away, close to infinity, the lens is in a relaxed state. It provides a flatter surface and a longer focal length for distant objects. And then as an object moves in, what happens is the ciliary muscles tense up, you get a greater curvature, a greater radius of curvature, or I'm sorry, a less radius of curvature and a less focal length. So this is for closer objects. Accommodation allows us to view objects from a far point, for most people, which is infinity, to a near point. A near point is a point where the closest point to your eyes that you can still see an image clearly. For young adults, this tends to be about 25 centimeters. But as you age, your muscles weaken, and that near point actually gets pushed out, which leads me to talking about why I'm really here is the problem with the eye is known as nearsightedness and farsightedness. Nearsightedness, or myopia, occurs when a sharp image is formed in front of the retina and you get a blurred object. What actually happens here is that a person can't really see a distant object very well until it starts to move in and it starts accommodating. And so what happens is the entire field of vision is actually moved in. You don't have as great a far point, but you also have a closer near point. Like I said, the image is formed in front of the retina, so what we need is a diverging lens to push that image back onto the retina so the person can have normal vision. There's also farsightedness, or hyperopia, and this has too little convergence, so a distant object is actually formed behind the retina. So what we need in this case is for a converging lens to pull that image forward onto the retina so we can see a clear image. Also, a lot of people have reading glasses as they get old. This is actually a condition called presbyopia, and this is the ciliary muscles weakening with age, so that near point actually gets pushed back because the object or our lens can't form that curvature to see a clear object. Alright, now what I've done here is we have a little light source and then what we've designed to be a representation of the eye. It's got a double convex lens in it, which is equivalent to our pupil. And as you can see here, this would be a normal eye with normal vision. And if I scoot it back a little bit, it becomes a little blurry, a little out of focus. And so if we put a diverging lens in there, it'll push that image back and form a clearer image. Now we can do the same thing. We can push the image a little bit further up so it's a little bit blurry, and then we can stick a concave or a converging lens in there to pull the image forward. And this is the same thing as putting on glasses. You either have a diverging lens or a converging lens that pushes or pulls the image forward or back depending on your symptom. Alright, now this might actually be a little bit easier to see. This is just the light source in a light box, and what I'm going to show you is how different types of lens and different combinations of lens actually alters the focal point. This would be just like our normal eye. This is what it does. It converges to form a single point, which we hope to be on the retina in normal vision. And if we add another, say this point is too far back, say it's behind the retina and we see blurred vision. If we add another concave lens, see how much that pulls that focal point up? Now this depends on the power of each lens and how bad your vision is. Doctors can prescribe different power lenses to focus that image on your retina. But if we also have, if you say that image is forming too close, it doesn't hit your retina, it doesn't reach far enough back, we can add a diverging lens which pushes that image point farther back, as you can see. This is the basic principles of optics of the eye and how the lens and the eye works.